Welcome to the Baltic Hackathon 2024, Bridging Borders. My name is Kira, and I am an AI prototype of the Lübeck University of Applied Sciences. In this screencast, we'll tackle hallucinations in AI-generated text, a significant challenge when using large language models. Hallucinations occur when AI models generate inaccurate or fabricated information. We'll explore innovative strategies like clever prompting and advanced retrieval techniques to combat this. These approaches can create more transparent, accurate, and reliable AI models, with implications for chatbots, virtual assistants, content generation, and language translation. Let's get started. Imagine asking a super-intelligent language model that has never seen the sky, felt the sun on its digital skin, or heard the sound of raindrops, "What's the weather like today?" What would you expect as an answer? Would it be a confident but completely fabricated response? "Oh, it's a beautiful sunny day?" Or would it be a hesitant, "I'm not sure, I don't have that information"? We've all seen it happen. Our language models are incredibly skilled at generating human-like text, but sometimes they get it spectacularly wrong. Let's never forget that language models don't think like us, but only complete text prompts. That's because they rely solely on patterns and associations learned from their vast training datasets. Now, consider this. What if we could enhance these models? What if we could infuse them with external knowledge to enrich their responses? I invite you to enter retrieval-augmented generation, a promising approach that marries the prowess of language models with the precision of retrieval-based systems. By tapping into external knowledge sources, we can craft language models that not only boast improved accuracy, but also offer greater transparency and reliability. Hallucinations and the lack of factual accuracy are two main challenges traditional language generation models face. These models are prone to generating incorrect information, harming the generated text's quality and reliability. Traditional language generation models predict the next word or character, which can produce incorrect information. For example, a model might say that Paris is the capital of Germany, which is grammatically correct but factually incorrect. Researchers have developed a new approach called retrieval-augmented generation to overcome these limitations. This approach anchors the generation process in accurate and verifiable facts, reducing hallucinations. The potential applications of RAG are very promising. This approach is used to generate high-quality texts in fields such as medicine, law, or finance, where factual accuracy is not just important but crucial. Moreover, RAG is used to improve the quality of question-answering systems, chatbots, and virtual assistants, making them more reliable and efficient. It has shown that integrating external knowledge retrieval into generative models can significantly enhance their performance on knowledge-intensive tasks. But what's actually changing? In a standard language model generation, you input a prompt directly into the language model, which then generates an answer based only on its pre-trained knowledge and the provided prompt. However, this approach has inherent limitations, as the response is confined to what the language model was trained on. This might not include the latest or most specific information needed for a precise answer. In contrast, retrieval-augmented generation changes this process by introducing an additional step. Instead of just giving the prompt to the language model, the prompt is also used to search an external data source, such as a database or search engine, to retrieve relevant context or information. This context is combined with the original prompt and fed into the language model. As a result, the language model generates an answer using both its pre-trained knowledge and the newly retrieved information. This method leads to more informed and accurate answers, because the language model can incorporate up-to-date and specific data. So, retrieval-augmented generation combines large language models with information retrieval systems, allowing it to access external databases in real time and making them more accurate and up-to-date. Unlike traditional models, retrieval-augmented generation's knowledge base is not fixed and can dynamically update without retraining, making it more memory efficient. However, What truly distinguishes retrieval-augmented generation is its ability to enhance contextual understanding by accessing relevant documents based on context. This unique feature allows retrieval-augmented generation to provide more informative and relevant responses. In conclusion, retrieval-augmented generation is a game-changer in natural language processing, offering more accurate, up-to-date, and contextually relevant responses. Okay, retrieval-augmented generation makes things better. But how does it actually work? At its core, retrieval-augmented generation leverages the strengths of several technologies, such as vector stores, embeddings, large language models, and prompt templates, to generate text that is not only high quality, but also more accurate, diverse, and informative. These unique features set the text produced by retrieval-augmented generation apart, making it a valuable tool in the field of natural language processing. This diagram represents a basic retrieval-augmented generation architecture. This architecture starts with the user inputting a query, which could be a question or a statement that requires an answer or further information. The query is then passed through an embedding model, which converts it into a high-dimensional vector representation. This transformation allows the system to handle the query in a format suitable for similarity search and semantic retrieval from the database. Embeddings will enable us to search semantically, meaning that when we search for sweet sandwich spread, we can find honey and jam, even if there is no textual match in the terms. Next, the query's vector representation is used to search a database, or to be more precise, a vector store index inside a database. The vector store index holds the vector representations of documents stored in the database, enabling efficient similarity search. Once the search is performed, the relevant documents or pieces of information are retrieved from the database based on the similarity search. This retrieved information is referred to as context. The context is then fed into a large language model, a powerful tool in our architecture, along with the original query. The large language model uses this context to generate a coherent and contextually appropriate answer. The generated answer, a testament to the model's capabilities, is then output to the user, addressing the original query. Let's take a look at this architecture block by block. We start with the embedding model. Embeddings are numerical representations of concepts converted to number sequences or vectors, making it possible for computers to calculate the relationships between them. Numerically similar embeddings are also semantically similar. For example, the embedding vector of canine companions say will be more similar to the embedding vector of woof than that of meow. This is because the relationship between these concepts is captured in how the vectors are positioned in a high-dimensional space. It's like a map where similar ideas and words are clustered, and the distance between them represents how closely they are related. Using these embeddings, language models can understand natural language, make predictions and classifications, and even generate text. Embeddings are a powerful tool that revolutionizes the field of natural language processing. Tokens and embeddings are fundamental concepts in large language models. A token, be it a word, character, or subword, is a versatile unit of language input. It forms the adaptable basis for understanding and generating human language. By processing these tokens, LLMs can uncover patterns, relationships, and context to perform tasks such as text generation and language translation. An embedding is a numerical representation of a token in a vector space that reflects its meaning and context. It allows a token to be represented in a numerical vector space so that its meaning and the context in which it occurs are taken into account. This enables the capture of semantic relationships between tokens and enables semantic calculation with the vectors. Examples of embeddings are the word representations of the words king, woman, and queen. As shown on the right side, these can be expressed as vectors and used for calculations. This example shows that with embeddings, one can capture semantic relationships between concepts like king, queen, and woman and thus calculate with them. For instance, queen can be expressed by adding the embedding vectors of king and woman. Okay, back to our architecture. Let us now turn to the second large block, the so-called vector stores. These utilize the embeddings just explained to search information semantically. But how does that work? A vector store is a database that stores a vast collection of vectors, each representing a unique text. These vectors are just high-dimensional numerical representations of the original text's semantic meaning. For illustration purposes, the vectors are visualized here in three-dimensional space. In reality, however, we work with hundreds or even thousands more dimensions, which of course impairs visualization. When we have a prompt or request, a vector store becomes a powerful tool. We can use it to search for the most similar vectors that match the context of the prompt, making it an invaluable resource for text similarity search. The most similar vectors have the shortest distance to the query vector, measured by a distance metric. Typical metrics include Euclidean distance and cosine similarity, where values close to 1 indicate high similarity. So, the most similar vectors are those with the smallest distance to the query vector, calculated using the selected distance metric. They represent the semantically closest text to the original query or request text. The vector store is populated and updated in a straightforward manner. We calculate the vector representations of each piece of text and store them in an efficient data structure for searching. When we add new texts or update existing ones, we simply recalculate the corresponding vector representations and update them in the vector store. There's a wealth of vector stores available, with almost every database now offering vector indexing as an option or addition, thanks to the rise of large language models. Here are just a few such databases. When selecting vector stores, attention should be paid to scalability and performance to ensure that they can efficiently process large volumes of vector data. Supported algorithms and compatibility with existing data infrastructures are crucial to ensure seamless integration and optimal utilization. Due to time constraints, I won't go into any more detail. But I have a shortcut for you. For hackathons, I recommend working with ChromaDB, especially if you are new to vector stores. If you are already experienced, feel free to use the vector store you are most comfortable with. However, we encourage you to leave us a note about your experience, as it can help us learn from your expertise and build a stronger community. Nevertheless, ChromaDB is a high-performance database optimized for managing and querying large volumes of vector data, commonly used in machine learning and AI applications. Its advantages include efficient handling of high-dimensional data, fast similarity searches, and seamless integration with various machine learning frameworks, making it ideal for applications like recommendation systems and natural language processing. One of the key strengths of ChromaDB is its versatility. It can be configured in various ways to suit different project needs. Whether you need a low-latency in-process, in-memory database, or a more traditional external database, ChromaDB can handle it. It also supports distributed, horizontally scalable architectures, making it a versatile choice for a wide range of projects. So you can start small and scale up. In-process and in-memory computing are often perfect for a hackathon, but your solution can scale out. Okay, back to our architecture. At this point in our journey, how do we get the query and the context we have semantically determined about the query into our language model? A language model only processes one query input, not several. We need to somehow embed the context into the query. But how? Large language models are powerful tools capable of generating human-like text based on the extensive knowledge encoded during their training. However, they face a significant limitation. They rely solely on the data available up to the point of their training. This constraint often leads to a phenomenon known as hallucination, where the model fabricates information when encountering a query outside its knowledge base. For instance, if you ask a large language model about the current weather, it cannot provide an accurate answer, since this information is dynamic and was not known during its training. We can retrieve additional contextual information from other data sources and inject it into the user prompt to address this limitation. However, the context must fit within the limited context window of the LLM. This method combines the strengths of retrieval mechanisms and generative models, leading to more informed and contextually accurate responses. To implement this technique, we use a structured prompt template that simply provides a placeholder for the context obtained from the vector store. It's pretty simple. That takes us once through our RAG architecture, and we have familiarized ourselves with the relevant technologies. Linus Torvalds, the creator of the Linux kernel, famously emphasized the importance of tangible results in programming with his quote, "Talk is cheap, show me the code." Being results-oriented is undoubtedly an advantage, especially at a hackathon. So, let's take a second look at our RAG architecture. But this time, we are focusing more on code. You know, it's a hackathon. We will take the same route through the architecture again. The good thing is you already know your way around. Once again, we start with the embedding model. This time, however, we are not asking ourselves what embeddings are, but how they can be used programmatically. This will be much easier than you think. We can play a little trick and use libraries developed specifically to develop language model-based applications, like LangChain, for example. LangChain is a framework for developing applications that combine language models and external data sources to generate contextualized and precise answers. This code snippet initializes an embedding model using the Hugging Face endpoint embeddings from the LangChain Hugging Face library, specifying a model hosted at a given URL. It then uses this model to generate a vector representation of the query, "What is prompt engineering?" using the embed query method, and prints the dimension and the first 5 elements of the resulting vector. This process transforms a query into a numerical format suitable for further processing in a vector store. This works perfectly if you only have one query that you want to convert into a vector using an embedding model. However, we usually have to process several documents when building a vector index. We can use embed documents for this, which saves us a loop, and the embedding model is also optimally supplied with the documents to be processed. So you don't have to worry about that at all. The library takes care of that for you. And on with the architecture. Here we are again with the vector store. But in this round, we are not asking ourselves what a vector store is, but how to use vector stores programmatically to build a knowledge base. This is more difficult than generating embeddings for queries or documents. The first step is to download your content. This means you collect all relevant information, documents, files, and data crucial for your knowledge base. This content can come from various sources, such as scientific articles, internal reports, research documents, or other relevant materials. In our example, we are building a prompt engineering chatbot that gets its knowledge from promptingguide.ai. Once you have downloaded your content, the second step is to import the relevant parts into your knowledge base. This involves selecting the most important and valuable information and converting it into a format that can be processed by the database. The actual creation of your knowledge database takes place in the third step. In this step, you organize the imported data to be easily accessible and searchable. This means, in particular, that you need to semantically index your models using an embedding model. The next step is to test your knowledge database. Here, you check whether the database also provides meaningful contexts for questions. If this is not the case, the selected embedding model is probably unsuitable for the intended purpose. A little research is then required. Finally, you link your knowledge database and your language model using specific prompt templating techniques. Let's look at these 5 steps in detail using the example of code snippets. Let's start with the first step. Our aim is to develop an expert chatbot on prompt engineering. We will use the content of the promptingguide.ai website to do this. After some research, we understand this page was generated from a repository on GitHub. That's good because these repositories can be downloaded. The code shown here downloads the repository as a zip file from the specified URL and then unpacks it into the current directory. This allows us to transfer all the necessary content quickly and efficiently to our local computer. In the next step, we import the relevant parts of the repository into our knowledge database. The necessary files are in the AR pages directory and have the extension .mdx. MDX is a format that allows JavaScript XML to be embedded in Markdown content. This is particularly useful for flexible and interactive document design. Let's look at the code. We use the recursive character text splitter to split the contents of the MDX files into smaller processable parts. The files are searched recursively through the rpages directory, and the contents are divided into smaller blocks of text that can then be imported into our knowledge base. The size of text blocks, or chunks, required for good retrieval. Augmented generation depends on several factors, including the specific requirements of your system, the type of data, and the performance of the language model used. Smaller text chunks of 500 to 1500 characters allow for more fine-grained control and more specific answers, but are more computationally intensive and can increase the number of queries. Medium text blocks of 1500 to 5000 characters are often a good compromise between detail and processing efficiency. Larger text chunks of 5000 characters or more are useful for broader contexts, but they can affect the precision of responses if they cover too many topics at once. As our database consists of articles focusing on exactly one topic at a time, we work with large text blocks of up to 10,000 characters. Now we just need to convert these chunks into embedding vectors and save them in a vector store. This is incredibly easy thanks to LangChain's integration of embedding models and a variety of vector stores. We use Chroma and work with a BGE M3 embedding. The code shows how this works. Essentially, this is done by the marked chroma.fromTexts call. The main advantage of the BGE M3 embedding is its multilingualism. BGE M3 supports more than 100 languages and is suitable for multilingual and cross-language retrieval tasks. It can process input of varying granularity, from short sentences to long documents with up to 8,000 tokens. In performance comparisons, see also the red arrow on the right, it performs very well and achieves results comparable to the commercial OpenAI embeddings. We therefore recommend working with BGE M3 embedding. And now we come to the fun part. We pass a prompt to our knowledge base to get hits of semantically indexed content chunks from the prompt engineering guide related to this prompt. Here, we define our knowledge base using the BGE M3 vector store as a retriever, with search parameters set to return 3 relevant documents. We then invoke the knowledge base with the query, "What is prompt chaining?" The loop iterates through the retrieved documents, printing their content and length. A LangChain retriever is a component that retrieves relevant documents from a specified data source to support language model operations, enhancing the model's ability to generate contextually accurate and informed responses. We are back, where we must bring context and query together. So we have to solve a final question. How do we programmatically get the context into our prompt? Our fifth and final step is connecting our knowledge base to the large language model. This code demonstrates how to use OpenAI's API to generate a response to a specific query. It retrieves context from a knowledge base and streams the reaction in real time. This is where we set the query to run through the language model. This line retrieves context relevant to the query from a knowledge base. The context is combined into a single string, with each piece of content separated by a new line. The parameter messages defines the conversation history. The first message sets the assistant's role as a prompt engineering expert. The second message provides the retrieved context. The context referred to above is inserted into the conversation history at the marked point and thus considered by the language model. The third message is the user's query triggering the language model answer generation process. The output streaming loop iterates over the streamed response and prints the content incrementally, enabling real-time output. That's it. These are the elementary steps for setting up a retrieval augmented generation. They're easy if you know the necessary components and their interactions. Okay, let's sum things up. Simply put, retrieval augmented generation can be summarized as embedding plus vector store plus LLM. By integrating these elements, RAG can access and utilize external data sources in real time, enhancing the model's responses with up-to-date and specific information. This means the model's output is based on its trained knowledge and incorporates fresh, relevant data from external sources. I wish you all the best in your future hackathon endeavors and encourage you to stay in touch. Remember, our support team is here to help you whenever you need it. Again, I want to remind you of the tools we make available to all hackathon participants. On our GitLab platform, you can work together, share code, and track progress seamlessly. You can also find your team repository there. Additionally, our Jupyter Hub platform offers interactive notebooks where you can experiment with individual code snippets and take your coding skills to new heights. The GitLab QR code points to the landing page where you can find your team repository. The repositories are ready to deploy the featured RAG-based prompt engineering expert chatbot. The Jupyter Hub QR code refers to a notebook that explains the code shown in this video step by step. Feel free to play and experiment a bit with this notebook. I look forward to seeing the fantastic things you will achieve in the following days. So, code strong.